So up until now, we have a lot of learning method, and this one is the most uh, modern one. Um, it's actually spark a lot of interest at the beginning, and then it's fall down a little bit, and then it's come back very strong. So a lot of AI today rely on neural networks. So we have to understand what is going inside the neural network so that we can build upon uh, what currently what we currently have. So let's start with uh, some history. Um, we are going to go back in time. So at the beginning, um, we have all these methods like support vector machine, have like decision tree. For artificial neural networks, it all start in 1940. Basically, people want to imitate a neuron. Basically, is a cell inside a human brain. Yeah, it's already recorded. Is it? Is it recording? I think I tap. Yeah, right. It's already recorded. Yeah, so people want to imitate a human brain because we are fascinated by our intelligence, how people can learn so quickly. So they want a computer to do the same thing. So we go back to biology. Um, in our brain, we have a cell called dendrite, right? We have dendrite, and then we have a neuron. And for each of these cells, what we have is each cell is connected, right? It's connected by an axon. And one neuron cell will send some signal, right? Maybe some action potential via an axon into a synapse. So synapse is a receiver. So another cell receives the input from another cell, and then it's gonna do some processing, and it will output something at its own axon, right? So each neuron cell, you can think of it as like a unit that receive input, do some processing, and spit out the output. Now, this output can be transferred into another cell, right? So each cell would have a different way of processing the information. And for us human, we have about 100 billion cells, right? 100 billion cells. This is equivalent to Intel Pentium 4 1.5 gigahertz. This is a very old model, right? Right now we have like i5, i7, i9. But back then we have like Pentium 1, 2, 3, and 4. So that was um, the top of uh, a computer at that time that can handle 100 billion cells. So how can we model this interaction for a computer? So in 1940s, we have Warren and Walter. So these two people are not from computer science at all. Actually, there's no computer science like knowledge at the time. They only have like mathematics or maybe a physician. So we have a neuroscientist and a logician. So what is a logician? It's basically people build a logic gate, right? You studying in engineering, so you probably have done some like logic gate building before, and they model a logic gate after a theory of how the neuron work. So each each cell, right? Each cell in the human brain is a logic gate. And depending on how you build a logic gate, you will get a different output, right? So we have the input. So in a normal logic gate, right, you would have like two input, and then it will give out the output. And one of the very first logic gate for like a neuron would be x1 and not x2, right? So that is like the very first way that they built it. So this one will always give you 0 or 1 because it's logic gate, right? It's going to be true or false. So true would be 1, false would be 0. Right? So this is our the very first neuron. Now in 1950s, we upgrade from a neuron. So we move away from a logic gate because logic gate is very limited, right? You can only have two input, and there are a limited number of logic type of logic gate that you can do with just two input. So we move away from logic gate, but we still keep the structure the same. We still have input, and then we have the processing unit, and then we have the output. Now in 1950, Rosenblatt introduced perceptron. So in the perceptron, right? So this node, right, the weighted subnode, this was a neuron, right? This was our original neuron. And this neuron is going to get a lot of input. It's going to get many input. And the function is only just to combine all the input together. And then we have some step function, and then we're going to split the output, right? So remember, we want the neuron to output 0 or 1, right? 0 mean inactive, 1 mean active, right? So our in the ultimate goal is to get this 0, 1. And so in the step function, right? In a step function, basically, it's going to be we will output 1 if input maybe greater than 0 and is 0 otherwise, right? It can be as simple as this, right? For the step function, right? You can substitute 0 with maybe some threshold, but normally you would just say 0. And this is also the first time that we introduce weight, right? So in the neuron case, right, in the neuron 10 years ago, we don't learn anything. People would build a neural network based on their intuition, right? So they have to think maybe this kind of gate will combine well with another gate, right? And this become quite a task for a designer because the designer has to understand everything inside um, the network. But in the perceptron, each input, instead of sending into the neuron directly, it will go to a weight. So each input will be multiplied, right? It's going to be multiplied to the weight, and then it's going to sum up, and then it goes to the step function to get the output. And the beauty of this is that because we only have one structure, we don't have to think much about the design. What we have to think about is how can we get this weight, right? What are the value of this weight? So when he proposed this type of neuron structure, he also proposed how to compute the weight, right? And the way to compute the weight is very simple. You can just use any optimization, right? Because you have this function, right? So basically, it's become down to weight transport time x, right? Basically, you have this x as an input, you multiply by the weight, and then you do the sum, right? So you get something like this, and you can just use something like gradient descent to compute the derivative of the weight, right? Compute the loss function with respect to the weight, and then you update the weight this way, right? Because you know if the output is incorrect, you try to change the weight so that the output would be as close to the answer as possible. So that is in 1950s, the perceptron. And then 20 years later, people start using perceptron a lot, and Minsky um, faced one problem, right? So for the perceptron to work, it will only work for the data that is linearly separable, right? Because it is a linear function, right? It is a linear function. And what happens if I want XOR gate, right? So when we need an XOR gate, we cannot just use uh, perceptron, right? How can we design the weight to have this kind of behavior? So basically, if either one of them is on, the output will be on. But if both on, the output will be off. If both off, the output will be off, right? So we have this kind of situation that no matter how you train your network, you will never get the XOR gate, because when you take the sum, right? If this become active, separately from this become active, you cannot deactivate when both are active, because you can only do the summation, right? So for the XOR gate, this become a huge issue. And when Minsky raised this problem, and what happened is that for the next 10 years, people will stop doing perceptron, right? Because they think that, oh, it's the end, right? It cannot do XOR, so there's nothing else to do. So in the next 10 years, there's no major development, right? There's no new idea. I mean, perceptron still being used in some cases, but it still cannot, break through the XOR problem. And then in 1990s, we have Rumelhart and Hinton. So these two design a new idea. And a new idea is basically a multi-layer perceptron. So what is a multi-layer? So basically in the perceptron, right, you have one node, you have one neuron, and then you get all the input, and then you will get the output, right? So that is a very simple perceptron. Now in their case, right, they build a multi-layer. So instead of just confine into one neuron, they organize the neuron into a set called layer. And then they put the network into multi-layer, right? So you have the input layer, the hidden layer, and then we have the output layer. And not only they propose the design, they also come up with two more, right? Two more novelty. The first is they introduce the nonlinear differentiable activation function. So before here, what we have for activation, so this is a activation function. Basically, what the output of the neuron come, you have to decide whether you get 0 or 1, right? And this was the step function. And as you can see, right, if I use this function, it's not differentiable at which point? Right? So if you have like the graph, right, you have negative 1 to 1, have 0, you have something like this, right? Right, so this is the function. And at 0 point, this is not differentiable. Right? So the step function is not differentiable. So they have also come up with a nonlinear differentiable activation function. And on top of that, they also come up with the algorithm to compute all the weight in the graph. Right? Because when you have a very big function, it's going to be very difficult to write down the entire equation of the network. Right? And then you have to do the different, you have to differentiate uh, the loss function with respect to each of the variable or each of the weights, and you have to update that, right? So that is quite a task, but they actually use some trick to update all the weights very quickly. So this is quite revolutionary. So at the beginning, like in 1990, when they proposed this multi-layer perceptron, computer scientists at the time is now split into two groups. One group is still want to use a traditional method, right? Everything have to have a human expert to build the network, to build an algorithm, and another group would just, you know, let the computer figure out the weight and let it do their own, right? So the difference is that when you have this type of network, right, what you have is number, right? This number doesn't is very hard to translate all this number into human intuition, right? Because it's all about calculation. So the two group of scientists, right, they want to understand what is happening, and another group just want to, achieve a better result. And fast forward in 2010, we have deep learning, and this is a pinnacle of neural network. So in 2010, Hinton, so if you notice the name, it's the same guy, right? So the same guy that invent perceptron, right? Upgrade his upgrade his multi-layer perceptron to have a neural network. And this neural network, not only you increase the depth, but also how to deal with millions of parameters, right? Because even with one hidden layer, right? Let's say you have 100 input layer, 100 node in the input layer, you have 50 in the hidden layer and maybe just one in the output layer. How many weights are in this graph, are in this network? So you have 100 in the input layer, you have 50 in the hidden layer. So the number of weights would be 100 times 50. So this is like 5,000 already, right? And then you have another 50 here. So with one layer, you already have like 5,000 parameters. And when you have multi-layer, right, you would have more weight, right? And if you follow the news about like OpenAI versus DeepSeek, you would heard the word like number of parameters, right? You have like a big model with like billion parameters, and then we have a small model with like a million parameters. So those parameters are the number of weight in the neural network. And since he introduced this type of network, people just using it, right? People start using this type of network. And not only that we have this structure, there is also some upgrade for each of the neuron um, to cater for specific application. And we will look into what upgrade can we do. So that is the brief history of the neural network, right? It starts from 1940s with a human brain, and then we evolved into perceptron, and then we got stuck with the XOR problem until we solved it with multi-layer perceptron, right? And we have SVM, right? SVM is basically a perceptron, but for classification, like in the middle, and then we have some deep neural network. So now that we know a little bit about history, let us define the neural network properly. So in neural network, we have vertices, right, or node, and these nodes are organized in layer, right, in layer, and any two set of vertices may form a bipartite graph. What is bipartite graph? Have you learned about graph theory? Any graph theory? So in bipartite graph, basically when you have two set of vertices, right? The bipartite graph is the graph that you only allow edge across the set. So between two sets, you can have edges like connecting to the network. But within the set, there is no edge. So that is the bipartite graph. And for the layer, right, there are three types of layer. You start with input layer, and you have the hidden layer, and you finish with output layers. So normally input layer and output layer would be just one layer. But for the hidden layer, you can have multiple hidden layers. So you can have like this here. So just to indicate that you can have more than one. And the set of weight, right? So the weight will be on the edges. And this weight will be the parameter of the model. And the learning part would be how you would learn all of this weight. So here's the example, right? In the input layer, we have three nodes. We have three vertices, right? And then we have two hidden layers. Each have four vertices. And then we have output layer with just one vertices. And notice the structure is that when you have an edge, you tend to have an edge from the left layer to the right layer, right? So you have like all the weight, right, connecting between layer. You don't have weight that go across the layer, right? You don't have this weight. This is to make the calculation simple. And for the input layer, it's basically the interface to the entire network. And the size, right? The size, how many vertices would be in the input layer will be based on your data, right? So how many dimension of your data, you would have the same number of input layer, right? Because when you feed your data into the network, you feed it into the input layer, right? So if you have three feature vector, the data with three features, each feature would get sent into one of each vertex in the input layer. So usually it can be the size of the parameter. And what about the hidden layer? So the hidden layer is going to add the capacity to the network. right? Basically, this network, this layer would act as some kind of learning inside the network. The more hidden layer you have, the higher the capacity, and more layer should be able to capture more complex relationship. And the number of hidden layer often referred to as a depth of the network. And the number of neuron in the layer, we will call the width of the layer. So here we have depth 2 because we have 2 layers, and each layer have width of 4 because we have 4 in each layer. And then for the output layer would be something that you get as the output, right? And the output should based on your problem, right? For example, if you want to do a regression, typically you will have one output node that will give you a number, right? It will be a number. If you have a binary classification, you will still get one output node, right? You will get 0 or 1 as the result, right? 0 would be one class, 1 would be another class. But if you have a multi-class classification, you would have multiple output nodes. Normally, you will have one node for each class. So you have like k node, right? For example, you have 3 classes. Like in the output layer, you would have t node, right? And each node will give you some number, basically correspond to, the property of this data belong to this particular class. So that is the basic concept of the neural network, right? You have input layer, you have hidden layer, and then we have the output layer. So what about activation function, right? Inside a node, right? Each node, you will get a lot of input, right? You get a lot of input. Now each input, you will take the sum, right? But not just the sum, but the weighted sum, right? So the weighted sum. And after you do the weighted sum, you will have to go to the activation function before you get the output, and this output will be sent to another node. Right? So that is what one node do, right? So one node will do two things. First, it will aggregate the input. The second is to use the activation function to decide what to send into the next node. And this activation function, the idea for it is that if the input is strong enough, I will send out some information. But if input is not strong, maybe I just stop sending information, I send 0. Right? So this is what the synapse of the human brain does. Right? If you don't have enough chemical reaction as input, it's gonna not send out anything as the output. And so we have a lot of activation function that you can choose from. We have the traditional nonlinear activation function. The very first function that we introduced when we use the perceptron is a sigmoid function. And the sigmoid function will have the function of this form, right? It's basically 1 to the 1 plus e to the minus x. And this is the very classic one. We can also have the hyperbolic tangent. Sometimes they will write it as tan h. right? This is a hyperbolic tangent. This is also another activation function. Now, for modern nonlinear function, we have rectified linear unit, right? And then we have the leaky version, you have the exponential version. So the difference between the traditional and the modern is that in the modern, whatever come before zero, right? Whatever less than zero, you try to not send anything besides zero. And then after that, you want to keep it quite linear. You want to keep the output quite linear. And in today, in today's standard, the rectified linear unit is the most common neuron type. So when you build a neural network, right, you have to specify the width and the depth of the network. And on top of that, you have to tell what type of activation function will be used for each node. And you can have different activation function for different layer. And this type of activation function, you will get in the hidden layer. For the output layer, you can still use step function, right? Because you just want 0 and 1. And after the first introduction of the neural network, we have many ways to build a network. And many ways of building the network can be categorized into 4 types. We have fully connected neural network, we have recurrent network, we have lateral neural network, and then we have partially connected neural network. We'll go to one of each briefly. So in the fully connected neural network, as the name suggested, for each node in one layer, it will be connected to every node in the next layer, right? So fully connected means you have all the possible edges that you can do, right? So this is the most common structure, right? If you don't know what to do, just use all the weight, right? The only downside is just the number of parameters. You have a lot of parameters from this. And then we have recurrent neural network. This recurrent neural network introduce a backward edge, right? So before we have edge from left layer to the right layer, right? So we send the signal one way. For recurrent neural network, we allow to have an edge from the current layer to the previous layer, right? So you can have a backward edge, right? So you can have a backward edge. And this will make the network more complex. And then we have a lateral network. So lateral network, basically you can have edge anywhere, right? There is no structure, right? You can have edge inside within the hidden layer, or you can have the edge between layer, right? So lateral means that these right, these edges are allowed, right? You're allowed to have to send information between layer. And then we have partially connected neural network. So it's basically fully connected, but you remove some of the edges. right? So you still send signal from current layer to the next layer, but not every node gets the input from all the previous layer node. And with these four types, you can design literally like infinite number of neural network. So at the beginning of the deep learning, like in 2010, like each of the AI lab would, crunching some architecture, right? And if you research the paper at that time, like in 2010, you will have like maybe 100 different um, neural network structure like per month in publication. So at that time, like people would just come up with new idea and so on. Our question become, how would you train the neural network? So remember, in neural network, we have parameter as a weight, right? And you want to train all of the weight in here, right? Because you don't know about the weight, right? You start with maybe random weight, right? And then you just set in the input, you get the output, and then you check whether the output is correct or not. But just checking doesn't help us with the updating. So we need to have some algorithm to update. So for the update algorithm, we have three approaches. The first is supervised learning. So what is supervised learning? Is the data we know the answer, right? So we have this input and then the output. And when we have the correct output, you can compare the output and try to update the weight so that the prediction would be as close as the actual as possible, right? So you can have some idea of how to update the weight. What about unsupervised learning? You only have data. You don't have the answer. Yeah. How would you update the weight when you don't have the answer, right? Um, we will look into this a little bit later. Uh, we also have reinforcement learning. Now, in reinforcement learning is a different type of learning where you would interact with the environment. And whatever you get from the environment is going to update the weight and inform you to do a different decision the next time you see the same environment. So, in the sense, reinforcement learning, you have the answer, but the answer is not given to you directly. It will give you, oh, you are better or you are worse than the actual answer. And our focus for today would be just supervised learning, but we will talk about the next two in the next class. So for the supervised learning, the algorithm to update the weight is called feed forward and back propagation. So in a typical fully connected neural network, the data will flow from left to right. We call this process a feed forward, right? You feed information forward. And this feed forward will generate the output, right? And once you have the output, you can compare with the actual, right? So once you compare with the actual, you will try to update the weight of this layer, right? So you compare this with the answer, and you will update the weight here, so that the input will be closest to the answer as possible. But you still fix the output, right? You fix everything in the network. You update the weight only the last layer. And after you update the weight so that the output will be as close to the answer as possible, then you start moving backward, right? You will update this weight, right? And you still fix, right? You fix this weight here, you fix this weight here, right? You try to change this weight so that you still get the answer as close to the actual as possible, right? And this is what we call a back propagation. So you update the weight backward from the last layer into the first layer. Now in unsupervised learning, right, you don't have the answer. So what people do when they want to train a network for uh, an image or the data, basically they duplicate the network, right? So you have, this is the input, right? This is the output, or this is the hidden. So we have input layer, we have hidden layer, and then normally this would be the output layer, right? This is the typical one. But if you don't have the answer, what we do is that we duplicate the hidden layer, and then we duplicate the input layer. Like you mirror it. And the goal is that when the data go through the network, the output should be the same data. And this process, what you get is you get the representation of the input, right? So this part, right, is going to be the encoder. So what do I mean by encoder? You have your input, you pass through the network, you get a new feature vector, right? You get a feature vector from here. And then you can use that feature vector for classification, right? You can use that as like in other classification algorithm. So this is a clever way, right? You basically you mirror your network, and your input and your output will be the same, right? So the intuition behind this is that you have the data, you compress the data into small number, and then you try to reconstruct this small number to get the same image, to get the same input. And if you can do that very well, it means that in the middle, your compact representation is good enough, right? So if you cannot get the input and the output to match very well, perhaps you might want to increase the number of neurons in the middle layer, right? So the middle layer is your feature vector, and if the number of neurons, the number of feature is enough, then you get a compact representation, right? So this is an encoder, and then this would be the decoder. And together we call it auto encoder. And then in the reinforcement learning case, we have agent, right? We have environment. And in the agent, you will observe something from the environment, you will observe something, and then you will convert the observation state into the internal state. And then you have this neural network inside, and then you take the action, right? And then the environment also give you the reward. So in the information learning case, you don't know the correct answer, whether or not the action you send is the correct one. But you know that the action that you send to the environment, you know the reward, right? If you have the positive reward, it means that, oh, this decision is good, but is it the best? We don't know, but it's good. And if we get the negative result, we know that the action that we do right now is not good, right? So we should do something else. So that is the reinforcement learning, and we will have the entire section for reinforcement learning. So let us look at the back propagation. How do we update the weight backward? So we start with a simple forward run, right? So if you have the data, you have x to be 0.5 and 0.1. So this to input, and your output will be 1, right? So if my input, right, let's say I get the input directly, you get 0.5 and then 0.1. You want this to be 1, right? You want this to be 1. So how should we compute the weight? So let's start with random, right? Let's start with random weight, right? Maybe I put 0.1, right, for every weight, right? Let's say every weight is 0.1, and let's see what are the number, right? So if all the weight are 0.1, what do I get in the first hidden layer? So you get 0.1 times 5, 0.1 times 0.1, and then you add up, you will get 0.01, right? You will get this 0.01, 0.06. And then when you multiply it one more time, and then you sum it up, you will get 0.018. And it is far from 1, right? So when we know that, okay, we have this hidden layer, the value of this hidden layer, we know that we want 1, but our answer is too small. So we want our answer to be higher, right? We want the answer to be higher. So we have to increase the weight, right? So there are 3 weights. You can increase them equally, or you can include them based on the output, right? So for this case, if you want it to be close to 1, right? Maybe you have higher weight, right? Maybe you have like close to 1, close to 1, close to 1, right? And then this will become 0.18, which is like closer to 1. And then when you fix this 1, you have to go back and trying to figure out this weight again. So that is the forward one. So how do we measure error, right? So the error is like the one that in the end, right? When we have this 0.018 and we compare with the answer with 1. So for the error, if you are doing regression, you can just use the square error. If you use binary classification, normally we would use the negative log likelihood. And if it's the multi-class classification, you would use the cross entropy. And for the classification case, you would use like sigmoid function or softmax function as the activation function. So these are called loss function. So you have many options for your loss function. And when you have the loss function, right, this is your objective function. And to update, right, to minimize error, right, you want to minimize the loss function, right? You want this loss function to be as low as possible, right? The ideal case would be 0, right? You want it to go down to 0. And if you want to use the gradient descent, right, what you need is you need to find the derivative of the loss function with respect to the weight, right? And the weight here, we have the ijk, right? So basically we have uh, which layer it is come from and which are the two nodes that connect for that edge, right? So you have three number for each of the weight. And the update function would become the O weight minus the learning rate. Like we learned this last time. This is the learning rate, the symbol for learning rate. And then you multiply by the derivative. Right? So you have this update function. What is the hard part of this plan? The hardest part of this plan? The hardest part would be to find the derivative, right? To find the derivative. Because like writing the loss function is actually quite a task, right? Like for this, let's say you have this type of network, right? Right, you have basically the layer one, maybe this, I will have this number for the node, right? So node 1 or 2. So we have 1 to 3 weight at layer 1 from 1 to 4, weight layer 1 from 1 to 3, 1 to 5, right? So I have all this weight, right? And what is the output, right? Like the output is the sum of each of the weight, right? Of the output of the previous one, and the previous one is the sum of the input of the previous layer. So you have multiple layer, you have like a nested definition of the function. And when you have a nested definition of function, when you want to take the derivative, it's going to become very messy. So we want to avoid writing down the entire equation and find the derivative of each of the variable, right? Because if we can do that, we can update all the way at the same time. But if we cannot, maybe we update one at a time. So the strategy is that, well, let us do the simple case first. And the simple case would be to solve one layer at a time. And so we need to find this, right? The derivative of the error with respect to the weight. But in the last layer, this would be in the last layer, this would be like very hard because the equation get bigger. So how do we solve this, right? So we want to find instead of finding this, we find something else that are a good approximation to this. And what we have is that we know that we can compute the derivative of the weight, right, in terms of in the next layer with respect to the final layer. So we want to use some chain rule, right? We want to use some chain rule because our equation is nested. So if we use chain rule, maybe we can make the chain derivative easier. So for the chain rule, right, you have a composite function, right? For example, you have g and then h, right? So basically, you set h you set x to h, and whatever the output you get, you set it to g, right? And then to take the derivative. Now for the chain rule, right? So basically you can take the derivative of just the g and then you take maybe one variable. And then you can expand this even more, right? To just derivative on h of x so that each part, right? Each of the three parts is easier to compute. And we're going to set up this very carefully, right? So we have the loss function. We have O jk to be the output of node j in layer k. And this is basically some activation function. So I would we pick a sigmoid function, right? Basically, you can pick any function that is differentiable. So we pick the sigmoid function, and the output of node j is basically the weighted sum of the previous layer, right? So we have this, we have layer k, right? We have the node j. The output is the ojk, right? The output is the ojk. And then this layer, you will get ok minus 1 and then I, right? Maybe I plus 1, I plus 2, right? So you have the output from the previous layer. And to get the ojk, right, you do the weighted sum. So this is the weighted sum, right? So you have from I to j, from I plus 1 to j for each of the weight, right? You do the weighted sum. And I will call this net jk. So net jk is the weighted sum at node j in layer k. And if I use the sigmoid function on this net jk, I will get the output. Okay. So n superscript k is the number of nodes in the layer k, and then we have this sigmoid function. So we have this setup, right? And now we can write the loss function as a function of each of these. So we have this loss function, right? We want to find the loss function, the derivative of loss function with respect to the weight from ij to k, right? So we have node j, we have node I, we have layer k, right? We want to find the derivative with respect to this weight. And so to compute this, right, we just have the intermediate variable, right? So this ojk is basically the output, right? It's the output of node j in the layer k. And this output, right, we do another chain rule. We introduce the network kj. So basically the net jk would be the weighted sum of all the input going to node j. So we have this chain rule. So if we can compute, right, if we can compute these three partial derivative, we can multiply them and get the answer that we want. So first, let's look at the red one. The red one is the partial derivative of the net with respect to the weight ijk. So here we can write the equation right? Because this net is the weighted sum, so it's the sum of the weight, right? And for all the input from other node, it doesn't matter, right? It becomes a constant when you take the derivative with respect to just one variable. So basically, you get OI at k minus 1. So the derivative of the weighted sum here with respect to this weight would be basically the input from node I at the layer k minus 1. What about the blue one, right? So the blue one, we want to find the partial derivative of the output, right? Want to find the output with respect to the weighted sum. And we establish that in a definition that is basically just the sigmoid function, right? So if we have the sigmoid function, right, we can take because these are the same variable, basically we take the derivative of the sigmoid function. And the derivative of sigmoid function, you get this type, right? So you get the sigmoid of the original network times 1 minus the sigmoid of the same network, right? You can do this um, by yourself. So we have a very simple, right, way to compute each one of them. What about the black one, right? The first one. So for the first one, there are two cases that we have to consider. The first case is, what if we are at the output layer, right? If you are at the output layer, you want to, get your final answer. So if you use the square loss, right, you would have 1 over 2 y minus the output of jk square, right? So this is the your loss. And if you take this derivative, you get the difference between the network, right? Between your output and the actual output. So this is the simple case when you are at the last layer. So what if you are in the hidden layer, right? You're not in the last layer, you are in the middle. So the OI, the OJK is basically the output to the next layer. So it will affect the square error through the net k plus 1 in the next layer. So what we have, right? We can write uh, this and use the chain rule, right? So the loss at the final one is the sum of the loss for each of the node in the next layer, right? And then you can use the chain rule uh, for this, right? So if you choose the chain rule for this, you will get uh, this type of equation. And you will finally reach this for the last layer. Because if you not in the last layer, you expand the chain rule, right? You get a similar equation, but now you get the loss of the next layer. And if the loss of the next layer is not the output layer, we will start this again. You start the chain rule again until this k minus 1 is the output layer. In that case, we use this one. we use this equation at the end. So for this case too, you have to use recursion, right? So basically you want to compute from back and then you start moving backward. Yeah, because to know the value of layer k, you have to know the loss, the derivative of the loss at the layer k plus 1, right? So if you know the k plus 1 from the output layer, then you can just use that value, right? So um, it's the propagation from the last layer into the previous layer. So the algorithm become, you start from the output layer, you update the weight, so the weight equation would be the same for every node. So if you start from the output layer, at the last layer, you would use the case one equation, right? Because you know this your output and this is the error. When you take the derivative of the error with respect to the output of the last layer. And then if you are in the intermediate layer, well, you use the same, right? You use the same equation, but this loss in the first term is become the weighted, it become the summation of the loss in the next layer times sum of the value of the next layer. But because you already compute all of this in the previous iteration, right? You don't have to recompute again, right? You use the answer from the previous iteration to plug in the value here, and then you can compute the new value, and then you multiply them together to get um, the derivative in the middle layer. So that is the back propagation algorithm. Right? You start from the output layer, you have this chain rule, you compute everything, and then you move on to the previous layer, you compute everything, but you also will use the result that you compute in the previous layer. So the learning challenge become the objective function with the hidden layer is non-convex, right? And you will encounter multiple local optima. So to prevent the local optima, what you can do is you can use the stochastic gradient descent. So what stochastic gradient descent does is that it will process, right? It, it will process the data by exploring the neighborhood, right? Before reaching the actual solution. You can also use something called momentum. These are physics, but you will move the objective, but you want to maintain the direction. So without momentum, you will find like the lowest the derivative. You move into that direction, and you will keep zigzagging. But if you use with momentum, at the beginning, you understand that, oh, well, you are going to do this way, but the next time that you move, you want to go this way, but you kind of combine both directions from the previous one. So you don't have to go up, you can go further into the function. Basically, you compute the gradient at each step, but your update function will use the gradient from the current step as well as the previous step. So this will help the stochastic gradient descent to reach the target quicker. You can also play with the learning rate. And I talked about it last time. Um, basically, we can use ADAM. Basically, is the adaptive learning rate. right? So if you have the learning rate that is very high, you will miss the local minimum. If you are too low, it's just going to take forever to reach the optimal point. But if you start with a very large weight and then you slow down, you would reach the optimal point faster. So you can use adaptive learning rate to update. Now, one thing about neural network is that depending on the data you have, you want to avoid overfitting. And if the network was left learning for too long, it will start memorizing the training data. So all the weight will be the memorization of what they have seen so far, and this cannot be generalized. So it's kind of like a counterintuitive because you want it to learn for a long time, right? Because the more it learns, the better the result become. But it will overfit the training data. When you see the new data that are far apart from the training data, you're gonna not gonna perform well. So there are a lot of technique, right? And the one that are the most common is called a dropout. So what is a dropout? So a dropout is that when you have a network, right? When you have a network, when you update weight, right? You will go to all the example at the same time. But instead of updating every weight in one epoch, we will randomly drop the weight, right? So for example, you choose the drop rate to be 50%. Basically, you will make all this weight become zero, and you will update the rest of the weight in that epoch. And when you come to next epoch, you randomize again. You randomize half of the edge to become zero, and then you update the rest. So this will help the network to not rely on the previous iteration too much, and will also help with the overfitting. But of course, you can also stop early, or you can use weight regulation. But dropout is the most common one. So before we continue with uh, convolutional neural network, uh, we will take about 10 minutes break, and we will come back at 10:25 just to take a breather to absorb all the information. Okay, welcome back. So previously we learned about neural network and the way that we design neural network, right? We have the input layer, we have the hidden layer, and then we have the output layer. So up until now, the input layer is a 1D array, right? So basically your input, your actual input will have to be 1D array. And the question is, how can we use neural network for the data that is not 1D array? For example, we have image, right? We have image, which is a 2D array input. So one way to use an image into our own neural network, we can do what we call a flatten, right? So the flatten, basically, you take each part and then you stick them into just one line, right? Just one line. But even though this will fit into our original neural network design, it doesn't make sense at all. That you would slide image and then you put them into a one line. Because when you look at image, you look at the pixel around it to be able to tell this is like some object, right? So we have like, for example, like if you want to have this correlation between the input here, it's going to be like here, here, and then maybe somewhere else down the line, right? So it's not in the consecutive one. So we want to have a neural network, but work on an image as is. Like we don't want to do the flatten because it will break all of the correlation between the pixel. So that's why we have convolutional neural network for just this type of data. So we use this neural network in a lot of visual recognition tasks, right? You have a neural network that can detect the monitor, maybe the stove, and so on. And to build a network for this type of recognition task for image, we need a new architecture. So in the past, right? In the past, when we do all of these recognition, we do something called feature extraction. And feature extraction is basically a handcraft algorithm based on human expert to extract some characteristic of the image. Right? For example, if you want to detect a ball, you would need somewhere to tell that, oh, there is this type of pixel, there is this type of pixel, there is this type of pixel, right? And if you collectively can detect all of them, then you can piece together information and then you can classify as a ball, right? So that is what we did in the past. And this work okay, it worked okay. But when you want to do something more complicated, right? When you want a complicated shape, you would need something more complex structure because um, our knowledge is limited, like how computer would understand the object in the image. And so we want to eliminate the feature extraction part, right? We don't want a handcraft one. So we replace it with just neural network. And this neural network have to do two things at the same time. It has to be able to extract some feature and also be able to classify the image. So because they have to do two things, we can try to have end-to-end convolutional neural network. So what do we mean by end-to-end? It means that when you design your network, the first half of your network would be something that help with the feature extraction part. And the second half of the network is going to be the network that you use for classification. So basically, you want to bridge the gap between two networks. And the gap is the feature layer. So when we talk about autoencoder, back a little bit. When we talk about like autoencoder, right? Basically, we want the first part to be your feature extraction for image. And the second part, you can use any neural network that you have been using for classification. And so in the middle part, right? Basically, it will give you a feature vector, but because you connect it with the classification network, you don't explicitly get a feature vector. So this is our ultimate goal, right? We have output, we have input, and then we have the network, and then we get the output. We want to do everything in one network. And to do that, we need something called convolutional neural network. And this neural network, this type of neural network will mimic the image. So instead of uh, having, so in the second part, when you want to do classification, you will do the one-dimensional array for each layer, right? So you do the same thing. But in the feature extraction part, we design each layer to be image. So basically what we have is that we start with image, we transform into another image, we transform to another image, and at the end, we transform it into just one-dimensional array. Now, each image that we did the transformation will not be the same image. The size is not the same. The depth is also not the same. And the way that we do it, we will use something called a filter or a kernel. So for CNN, right, instead of input layer, hidden layer, and output layer, we have convolutional layer, right? This one will be close to the image. And then we have the pooling layer. The pooling layer will try to make the image into one-dimensional array. And then we have fully connected layer. That will be your classification network. So that is the structure of the CNN. So how do we do the first layer, right? So in the past, when we want to detect a pattern in the image, we filter the image with that pattern. So we have a kernel, right? You have a pattern, and you want to find where this pattern is in the image. And what you do is you filter this kernel with the image. You get a response. You get one output, which is the response, and the location with the highest response will be the location of that pattern. So how to get this output? Basically, you design a kernel to be the same dimension as the image, and then you do a pairwise multiply, right? You multiply, you do the pairwise multiply, and then you sum it up, you will get one number, right? And this one number will represent the location, the response location at that pixel. So the CNN is basically the filter is actually learned from data, but you can also predefine the filter. So these are the predefined filter. We have the Sobel edge detection. We have two types. We have horizontal type and vertical type. And the way that you define a kernel is that the sum of all the weight must be equal to 0. Right? If you have horizontal, if you sum all the number, you will get 0. And this horizontal will detect a horizontal edge. Right? So what are the horizontal edge? Right? So we have, let's say we have the edge that would be like 0, 0, 0, 0, 0, 0, 1, 1, 1. So if you think of the image as the black and white image, right? You have this black pixel, and then you change it to the white pixel, right? So from black to white, you have yes. And if you pass this through this filter, right? You will get what number will you get? So on the left side, you have all the 0. So if you multiply pairwise, you will get 0. On the right side, you have 1, 1, 1. So you have 1 times 1, 1 times 2, 1 times 1. And then when you sum it up, you get number 4. Right? So this type of image, you will get 4. What about if I have this type? Right? So basically, I have a different type of edge. Right? So I start from the black on the top and then the white on the bottom. And then I have this edge, right? But this edge is not the same one as this one, right? This one is like up and then this one is down. So if I filter this, the same kernel to this image, which number I will get? So the top one, the top two row, you get 0. So you multiply them, you get 0, right? And then the bottom one, you have 1, 1, 1. So you have 1 times minus 1, 1 times 0, 1 times 1, and then I add up, I get 0. So each kernel will detect one type of structure, So this one will detect something like this, like something like the line in the vertical, and the one on the right would be the horizontal. So actually, the name, I think the name swap, if I'm not mistaken. So this kind of like the filter that you can apply on the image, and if you have the higher number, right, it means that you found the pattern that this kernel is responsible to. So from ImageNet, so the CNN, we learn all this type of kernel. as you can see, we also have like a typical like vertical line, horizontal line, maybe the line at the angle. We have the slight angle, right? So there are a lot of kernel that you can use for your network. So we learn how to filter an image. How can we construct the network? So the output, when we have the kernel, right? We have, let's say we have the kernel like 2 by 2. We look at the input, right? The input can be like 4 by 3. So you filter the kernel with the inputs that are confined to the same dimension. You get one number, and then you slide over, right? You slide over each pixel, and then you get the number for each of the filter. And that's and therefore the output you get will have the same structure. It will not have the same dimension, but it's still going to be 2 dimension, right? So if you have 4 by 3, when you filter 2 by 2, you get 3 by 2, right? So basically, you filter an image, you get another image. And this, we can use this to construct our layer. So we have input image. Let's say we have 32 by 32 by 3, right? So we have width and height, and then we have the dimension, right? So image would be, the color would be RGB, right? So you have one channel for red, one channel for green, one channel for blue. And the filter, basically, we have to keep the depth the same. We try to keep the depth the same as the image, but the width and the height, you can pick any number. And typically, width and height, we will choose to be an odd number. And the reason that we pick an odd number is because we can look at the center, right? There will be the center of the edge, and it's easier to understand. And so we have this filter. So when we do a filter, we also do the same thing, right? We have this 3 dimension. So if we do pairwise, right? We do pairwise, and then you sum up, and then you get one number per filter, right? So you do this for every possible position in the image, and you get the new image. So one filter, you get one channel. So if you have 10 filter, you would have 10 channel, right? You have the new image with 10 channel, right? So you start with 3 channel, and then depending on the size of your filter, you will get a new image. But this new image will have the number of channel equal to the number of filter that you apply to the image. So, okay, so I talk about this, like feature always extend to the full depth of the input volume. So when we do one filter, right, let's say I have 5 by 5 by 3, basically you do the dot product at every position, and then you take the sum, right? So you have about 25 dot product. So you do 75 dot product, and then you add it. You can also have the bias term. It's basically a constant that you can add after the filter. And so this weight and the bias, these are your parameter of your model. So when you learn the parameter, you basically learn the filter. You learn the filter. And if you have 32 by 32 and your filter is 5 by 5, what you will get 28 by 28, and then you have one depth, one channel, because you only apply one filter. So one filter will have one channel. And if you have 10 different filters, you would have 10 channels of the image. Right? So if you pass the green filter, you have another channel. So if you have 6 filters, you will have 6 activation map. So basically, we convert one image to another image, right? But the new image has different width, have different height, and also different size. So when we filter image, right, we can move 1 pixel at a time, but we can also move 2 pixels at a time, right? You can pick the stride. So the stride is how far we move, right? It's basically the sliding window size. And the more stride you have, the smaller the output image will be. Right? So we have another parameter that you can try. Right? This is the stride. You can also introduce padding. So what is the padding? So the padding is that when you have the image, right, you cannot filter past the edge of the image. So if you cannot pass the edge of the image, because the number outside doesn't make sense. What you can do is you can add a 0 to the outside so that you can filter the edge of the image. So if you have a padding, the output will have the bigger size compared to the input. Right? Basically, we increase the input by the padding. So after we do the convolution, we have to perform pooling. So what is the pooling? The pooling is the compression of the input. So basically, we have this activation map, right? Basically a new image. But this new image, it may be vulnerable to slice movement, like small transition. Like for example, like this image can be like one pixel off. So what you do, you look at the local window, you take the maximum, right? You take the maximum for each of the small window, and then you create a new image. So max pooling is basically you want to reduce the size of the image by taking the maximum on a small region. And then at the end, when we have fully connected layer, this is going to be the same layer that we had before. This layer will be for classification. So the output from the convolutional layer, right? So after the pooling, after everything, you can think of it as a feature. Right? You can think of it as a feature, and this feature can be used for other algorithm as well. Like if you don't want to use neural network for classification, you can use this feature for other like SVM or linear regression. There is also um, transfer learning. And this is some of the technique that help training faster. So what happened? So basically, when you have image, right, you make a model, you make a neural network to classify for one thing. Like let's say you want to classify for dog, right? So you have your neural the CNN for dog. Now you want to build your CNN for cat. You can start over, right? You start with random weight, and then you feed a lot of cat image, and then try to make it classify for cat. But maybe we can use some information from the dog to cat. And that information lie in the convolutional layer. So when we train for dog, we train both convolutional layer and fully connected layer, right? We train both. But when we train for cat, we just copy the weight from the convolutional layer to here, and then you fix all the weight in the convolutional layer, and you only train the fully connected layer for cat, right? So basically, okay, let's see if I have the image. So basically, we use the same. We use the same convolutional layer, but we only learn this part. And this become common for image, for computer vision, for image classification. When you want to classify a new thing, you don't start over. You use what people already have. Basically, you use pre-train. But the pre-train you use only the convolutional network part. And when you train for your own data, you will change only the learning part, the fully connected part. Because the this part, right, it doesn't change a lot. It's basically the feature extraction. And this feature extraction is generalized enough that it can work for all kind of images. So that is the beauty of transfer learning. You don't have to learn everything from scratch. You can copy the weight. When you train a new data, you fix the weight that you copy, and then you learn the new weight. So one of the most popular CNN for image is called AlexNet. So this is the architecture of AlexNet. So we start with input image. So this will be your input image. And after the input image, right, you have a, you have a filter that is 11 by 11. Right? It's basically 11 by 11, maybe by 3. And then you pick the stride of 4. So you move 4 pixels when you filter the image with the kernel. And then you get this image 55 by 55 by 96. And then you also use the max pooling. So the question is, how many filter does AlexNet have in the first layer? Right? So we know the size of the size of the kernel, that would be 11 by 11 by 3. How many kernel do we have for the first layer? Can you figure out from the image? So when you have one layer, so when you have one kernel, you filter this kernel into the image. you will get one channel of the output image. But this output image, how many channels does it have? It have 96 channels. So basically, you have 96 filter in the first layer, right? 96 filter for the first layer. And so if you multiply out, right? Let's try. If you multiply out 96 multiplied by 11 multiplied by 11 multiplied by 3, right, you will get about this many number of parameters. And after the first one, you do again, you do the filter again, but this time you have 5 by 5. But because this image has 96 channel, your filter has to be 5 by 5 by 96. Right? So this is the filter in the second layer. And how many of these do we have? We need to have 256 of these, right? Because the output of this convolutional layer, you have the image with 256 channel. And then in the next channel, you also have 3 by 3. So you would have to have like 3 by 3 by 256. And then you would need 384 for this. Right? And then you would do the same. Right? You would do the same. And once you reach this point, once you reach this layer, you have 13 by 13 by 256, right? So these are the number of pixels, like number of numbers in the image, and then you do the dense. So this then means that this 13 by 13 by 256 will be connected to all the 4096 neurons in the next layer. So this become fully connected. And then in the end, you will get maybe 1000. Like this will be your output layer. And why 1000? Well, it depends on your task actually. For AlexNet, they want to classify 1000 class. So that's why the output, they have 1000 number. But if you want to only use for like 3 classes, then your final would only have like 3 neurons. So this is how people construct a neural network. If you want to use AlexNet with your transfer learning, basically you fix all the weight up until here, right? You fix for transfer learning, right? So these are all the convolutional part, and this one you have to learn. You have to learn by yourself if you want to use transfer learning using AlexNet. So if you look at the recent paper for like image classification, they will tell you how they construct this part. Because this part, they will use the existing pre-trained convolutional layer from maybe AlexNet or ImageNet or like other network that people already train for you, and they will only change this part. So they will explain how the later part is constructed. So that is for image. What about text? Right? What about text classification? Now, for text classification, we need to understand context. Right? For example, I have the word like I love ice cream. Right? I have like 3 words. I have 4 words, and the word, the previous word, have some influence on the later word. So I need to be able to capture the flow of the sentence, right? Because what we learned before, we treat every feature the same, right? We treat every feature equally. We don't care if the feature is flipped, you still get the same result. But for text, if you flip the word like love ice cream, it doesn't make sense, right? It doesn't make sense. So position of the word, position of the feature, we want to maintain this relationship. And so we have to come up with a new way for a neural network to maintain this kind of relationship. And this type of data, we use what we call a recurrent neural network. So for the recurrence, right, we have this type of structure. So we have X. So X is the maybe one data, right? And we feed in the data bit by bit. And the output of the previous data will have some influence on the next data. So the data will have the time stamp to it, right? This can be word, this can be sentence. You can feed sentence as the data, right? And the sentence that you feed, it will have the order. So if you unfold this neural network, we have this extra structure, right? We feed in the input, the data from the current timestamp. We receive the output from the previous timestamp. And we want to combine them to output for that timestamp. And we also have to send the output to the next timestamp as well. So this will capture the flow of information because the input of the current timestamp, the current sentence, will have some information from the previous sentence or previous word. Now, one issue with the INN, with the typical INN is that when you have a long sequence of data, if you keep passing through information, some old information still persists, right? For example, this X0 might have some influence at the time H3 plus 1, right? So your first sentence of the paragraph can have an influence on the first sentence of the next chapter, right? If you keep training it like this. So we want to limit the information flow. We don't want the information to we still want the information to go to each timestamp, but but we don't want to keep it for too long, right? We have to have some point when the information drop off. So we have invented something called long short-term memory, LSTM. So LSTM have this mechanism of forgetting. So what do we mean by forgetting? It means that when you pass in the information from the previous timestamp, you can choose to remember or you can choose to forget. There is this mechanism that you can gatekeep the information. And in a nutshell, you have the structure like this, which a lot of neuron inside it. And we will unfold one at a time. So we start off with the memory lane. So what is a memory lane? The memory lane is basically all the information, right? So we have information coming from the previous timestamp. And we want to pass this information into the next timestamp. And in this memory lane, we have two operations. We have multiply and we have addition. And each operation serves different purpose. For multiply, you can pick whether or not the memory, your memory that you get will be passed to the next timestamp. If you multiply 0, it means that you forget. But if you multiply by 1, you will remember everything. And if you remember by 0.5, it's basically you just remember part of it, right? So this multiply can control how much information from the previous timestamp to influence the current timestamp. What about addition? What about this plus? Well, this plus will decide, right? So in the current node, we have some computation, right? We have some computation. And after we finish the computation, we get the output. And this output will be combined with the memory, right? So it's basically the memory of the current timestamp that we want to add into the memory lane. So that is the first part, the memory lane, right? You can forget your information. You can also add the current result as a memory. The next one is the forgetting gate layer. So what is the forgetting gate layer? The forgetting gate layer is the value between 0 and 1. Normally it takes the current input and the output from the previous layer. So these two things combined, it will decide whether or not to forget the memory from the previous timestamp. And the function is of the form, you have this weight, right? You multiply the weight to the two input, right? One input would be the input from the previous step and then the current input. And then you have some bias term. So that is the forgetting layer. And then we have the input gate. So the input gate, basically you do the weighted sum. So this weight will be different from the forgetting gate. So once you do the weighted sum, you have the sigmoid function and the hyperbolic tan function, and you combine them, right? Actually, you multiply them. You multiply them, and then you try to add this into the memory rate. So this is the calculation for the current timestamp. And the input from the output from each one of them will be added to the memory lane. And then the last one, we have the output layer. So the output layer is basically the weighted sum, right? You get the output from the current data and the previous output, right? The current data and the previous output, you combine them, and then you just put it into your new output. So that are the all layer that we have. And if you want to do the calculation, there is this code that you can try. Basically, it will tell you the output of each time step and the output of each node at each time step. So once we have the LSTM, we can start putting them together. And depending on your application, the way that you put them together will be different. For example, you can have like one to many. Basically, one connected, one LSTM will be sending signal into a multiple LSTM. Right, this is common in the image captioning. If you want to use post tagging, basically you have the many to many. The post tagging is basically you tag each word to be like subject, verb, object, adjective, and so on. Right? So you can have multiple ways to combine LSTM, and all of this will be used for text. Right? Image captioning, right? You have image, and you want to generate a caption for the image. But how do you train LSTM? There is a way to train based on calculus, right? You take, basically it's the partial derivative that we did for the neural network, but it's more messy because we have a lot of part, and you still want to use the back propagation, right? You want to update maybe this part first, and after you update this part, you update the second part, and then you update each one of the input at a time, right? And the calculation, someone did it for us, so we just take it as the correct. We don't want to, I mean, someone already proved it, so we just use it, right? We don't want to go into much detail. But the main algorithm is still back propagation. You update the LSTM from the previous one into the current one. But because it's not just a linear layer, you have to do all this calculation. So to summarize, we actually learn neural network, right? We learn CNN, and then we learn LSTM, right? And this should cover most of the application of the neural network, right? So if you want to use neural network in your project, you will pick one of these three based on the data, right? You have text data, then you would use LSTM. If you have image, then it's going to be CNN. But if it's anything else that is one-dimensional array, then you would just use the regular neural network. So inside that neural network world, we have generative adversary network. And this is the one that spark the generative AI. So this come before Gen AI, is the starting point of Gen AI. And what generative adversary network does is that it want to estimate the probability distribution of the data from just training example. And what they have is that they want to generate artificial image from just random image. So they would have two network, right? Two neural network. One network would be the discriminator. And this network, the purpose of this network is to learn from training example to detect fake or real image, right? So in your data set, you have real image, and then you have fake. And then you create a discriminator as a neural network to train on the data to check if the image is real or not. And then we have the generator. This generator will try to generate fake image from random input vector, right? So we have the generator, we just use random image to generate an image. And this image will be sent into the discriminator, and this discriminator will predict which image is real, which image is fake. And the way that we train both network, right? We train this discriminator to maximize the correctness, like the accuracy. And then we train the generator to minimize the accuracy, right? So basically, the discriminator want to classify as best as it can, but the generator want to create a fake image such that the discriminator think this is a real image. If we write it in mathematics, right? The dx, the discriminator, it want to maximize the cross entropy between the real image and the fake image. So it should accurately classify real versus fake. But the generator want to minimize the entropy of the property of X being generated. So it want whatever the image is generated, it want the generator to predict that is the real image. So they want to minimize this, right? So it become a adversarial game between the generator and the discriminator. And these are some of the results that you can get, right? So it's kind of weird, right? It's not dark, right? It's just some weird generated dark. But most of the classification would think that it is a dog, right? So that is something that the generative adversarial network does. And this sparked the idea of the generative AI, because we can generate this image, maybe we can generate it better based on the prompt. And then we have the Gen AI for the next generation of AI. So this is all the information about neural network. So we learned a lot of network, and it's better to go back and review some of them on your free time. We are not going to write code today, but hopefully next week we will have time to uh, start implementing the neural network because we there are a lot of steps that we have to uh, set up to be able to train the neural network correctly. And there are many libraries for neural network that doesn't seem to like each other. So we have to maybe pick one and stick with it. So in most cases, right, when you go to different laboratory or different teacher, each one of us will have one favorite neural network library, and we will only use this one because it worked in our case. And if you want to use different one, the professor cannot help you because they only know one, right? So we have like Keras, we have TensorFlow, we have PyTorch, and then we have like many more, right? So um, if you want to be like well-rounded, you have to learn all of them. But if you are professor only use one, just learn one. Okay. So that's all for today. I will see you again next week. Thank you.